Hello, and thanks for joining me today at Cyber Llama Talk. Today, we're going to continue talking about machine learning algorithms and specifically supervised machine learning algorithms and models in a period of time between 2005 and 2010. And specifically, we're going to continue looking into logistic regression as an example of such algorithm. Our focus today is going to be on feature engineering and feature development for algorithms like logistic regression to show how quality of such features in anti-malware product would directly impact and still directly impact result of analysis. Let's start where we finished last time. We talked about a few different types of features. First type of features I called primitive features. And the reason they're primitive because they're extremely easy to extract. Most of the time, they would be directly extracted from P header, for example, for executable files. It could be entry point. It can be a calculated entropy of the first, second, third section of the file. So it's not necessarily directly P header, but it's something very easy to compute after you parse the P header. And also it could be a number of sections. So it can be entropy of the first section name or a bunch of other primitive features. Those type of features, easy to change by malware. However, they might represent certain type of structure and they're easy to extract. The next type of features, previously called strings-based feature or API names-based features, that's when the engine would analyze the file, executable file, and extract everything what looks like string, and then filter it against a certain list of interesting string, which by some reason we consider interesting, and add it as a feature into our model. It can be a certain parameters of API function. It can be parameters of the network connection. It can be an API function name, which can be extracted either from an import table, or it can be, for example, just a name which is used to dynamically resolve import. Those type of features, they're string-based. They require a little bit more elaborate work to extract, but more importantly, those type of features are probably more relevant for unpacked files. If the file is packed by a protector or packer, those features would probably not be available at large, might be not available at all, or packer can actually masquerade itself as a benign software, and those features would not be very meaningful in this case. So those type of features, while they expose potential functionality of the executable files, they only work well if you actually apply some sort of unpacking techniques like a proto simulator or memory analysis before you extracting those features. Last but not least, the features which are more complex, and one example of those are n-grams. That means that's a feature which is based on a sequence of certain type of events or certain types of characteristics. For example, a sequence of API calls can be one example of n-gram. For example, 3 API calls which goes in sequence, or sequence of instructions can be another n-gram type of feature. It also might be more sophisticated feature which not based on n-grams, but they are based on code analysis. So when file is disassembled, we can perform certain code analysis and calculate characteristics like a frequency of certain instruction or distance between certain type of instructions and so on. So even though it's not necessarily n-gram, it can be more advanced feature which represents some sort of quality of the code or functionality inside the malware files. So why is that so important to distinguish between these type of features? We will talk in a second. But it's also very important to understand where we're extracting those features. For example, as I mentioned before, strings-based features would probably work well on unpacked sample, but wouldn't work well on packed sample. The code-based features could actually work for both examples. And just to demonstrate that they can be extracted both from packed and unpacked sample, let me show you this example. Let's say we have a packed polymorphic sample, which using a spaghetti-based code to obfuscate and hide decryption algorithm and make it very difficult to analyze the code. What it means is spaghetti code usually represented by a bunch of jumps. So the code is split on small pieces, like a few instructions, by jumps. And the code can be spread around all over the file, right? So when you try to analyze it, that's why it's called spaghetti code. It all just jump, few instruction, jump, few instruction, call, few instruction, and so on. So it's a lot of branching happening. And also to obfuscate and make it complex for proto simulator to emulate through this spaghetti code, it can call certain number of API calls here, just to make it harder to emulate because it can expect certain return value from these APIs and incorporate it in the spaghetti code. While analyzing that code, one type of data we can extract is how many instructions, right, number of instructions between two jumps. So average number of instructions between two jumps being executed or two branching instructions, right? It can, let's say we would assign that to A6. What we can also do is statistic of certain API calls. If we know that certain packers abuses certain type of API calls, we can compute on average time the sample calls the API, and we can also compute overall number of API calls in the sample, right? So then we kind of have a overall number, how many APIs were called. It's probably going to be a pretty low number when we're talking about disassembling a packer, but we also would see what kind of unique APIs it's called. So that could be this advanced code analysis features for packed file. For unpacked file, it's even easier, right? Let's say we're talking about a downloader or dropper. We can easily think about, for example, create file followed by create process, a type of n-gram, or for example URL download followed by create process, and it can go on and go on, right? You can find some n-grams, 2 grams, 3 grams of the API functions which are usually typical for certain type of malware, and you can add it as a feature as well, and that would work really well to potentially really well to represent certain type of malware if you already unpack the file and extracted those sequences of APIs which called by a payload. And in the period of 2005 to 2010, under the polymorphic packer, the malware authors were heavily relying on the polymorphic packer. So under polymorphic packer, as soon as you remove that layer of protection, the code typically would be very straightforward and easy to disassemble and easy to build that sort of n-gram of the instructions. So again, those more complex type of features could work for both packed and unpacked samples. Of course, they have to be designed with that thought in mind that you want to design some features which work for packed samples, some features which work for unpacked samples. But as we're going to see later, those are most interesting feature type of engineering, and there are a lot of, it really just limited by your creativity. What can you combine together to create those features? So why those features were very important? Let's deep dive into that. I actually love logistic regression as an algorithm because that's a great example of why feature selection and feature engineering is such an important task, and it was such an important task in 2005, 2010. It's still a very important task when you're working on classic machine learning approach and a classic detection or classification algorithm. So the way logistic regression works specifically, there would be a weight which associated with every single feature. So the feature would be normalized, multiplied to that weight, and then the result of multiplication summed up. And let's say here we have this z as an intermediate result of that sum. And then that sum would be passed into a sigmoid function. There's a little sigmoid here. And then the sigmoid would output the value from 0 to 1. And that value can be interpreted as a probability of how likely the file classified as malicious. Let's say the 1 would mean malicious and 0 would mean benign. It's very, very simple. The algorithm is very primitive. And so we have features, we have weights, we're summing them up, we apply nonlinearity, and we're getting a result as a probability of 0 or 1. And such algorithm would be initialized randomly. So all the weights would be initialized randomly. And then during the training, and that's another amazing thing about logistic regression, it's a really great algorithm to learn machine learning from, especially supervised machine learning, is that during the training, it's going to rely on a gradient descent and backpropagation to update the weights. So every time it will compute the final results on a batch of samples, it would compute the error and the cost of that error. And it would compute the gradient descent values, the gradients of how it needs to adjust each weight to improve overall, the reduce overall error. And it can repeat 100 to 1,000 times depending on the training. And it goes over and over and over. At the end, it tries to compute the optimal values for those weights to separate our collection of files into two categories, malicious and benign, with the minimum amount of error. It's very interesting that this picture can also be represented like this, specifically z. What z really is 1 plus a1 multiplied by w1 plus a2 multiplied by w2 plus what's going on, and it ends in a w. And I really like that representation, because if you look at this representation, it really gets very clear what logistic regression is. It's a weighted sum of different features, which is pretty much what heuristics used to be before machine learning, right? Before applying machine learning, what virus analyst would do, it would identify some interesting features, and it would say, oh, if those features are present, then each feature would have certain weight, and then we sum up final weight, and if weight is higher than a threshold, then it's malware, and if it's lower than threshold, then we cannot detect it. And usually those thresholds and weights would be computed manually, and it would be a pretty hard task to do, because you would compute one, and then you have false positives, you update your weights, and so on and so forth. Logistic regression pretty much solved that problem completely, right? Because if you have logistic regression, you don't need to think about weights you apply for every feature, because that's what logistic regression would do for you during the training. What you need is the collection of benign and malicious files. And of course, by itself, getting the collection of benign, a large collection of benign and malicious files between 2005 and 2010 period of time were not that easy. It wasn't a cloud time period where all the files were uploaded somewhere all the time. Internet was pretty slow and expensive still for that type of purpose. So, and antivirus companies had not had a legitimate way to easily collect files. Usually they would just collect files they receive from a customer, or for example, they would collect files which they can collect from Windows installation or very popular software packages installation, or maybe they would write a crawler to download things automatically from the internet. Again, download executables of the most common browsers or top 100 packages of the software and so on to crawl and download it. So then they can train such machine learning models on it. But the collections themselves were still a problem, right? Representative collection. But besides that, I want you to look at those features. As we said, A1, A2, A3 is a very primitive features here, right? It's those basic header extracted data. Now, let's say we only have the primitive features. How well do you think it's going to work? If you represent, for example, feature 1 and feature 2, A1 and A2, and let's say you plot malicious and benign files, and this feature is entry point, right? It's going to be a complete mess. And what logistic regression needs to do, let's say we choose 0.5 here as a threshold, right? After 0.5, it becomes malicious. Below 0.5, it is benign. So what we can say is, okay, what if z is well, y would actually be, in this case, y would be that sigma of z, right? So we can compute z would be 0 in this case. So if z is 0, what values A1 and A2 needs to have to split those set of files using a linear function, right? Because it's just a linear function. In this case, we would have 0 equal 1 plus A1 W1 plus A2 W2, like that part, right? And here that would be 0. So that very simple linear function have to separate this selection of files. I mean, how are you going to do it? Like, let's try it here, right? If you draw a line here, you have misclassification. You draw a line here, you have misclassification. You draw a line here, you have misclassification. It doesn't matter how you draw the line. So it doesn't really depend how well you will try to train the machine learning here, because the features are crappy and they're not separating benign from malicious. They're not evil bits, sort of say. You cannot, it doesn't matter that you apply machine learning, it's just not going to work. So that example of very poor features, and that's why those type of features were actually never used in logistic regression, because they would just be waste and the noise. They would not produce any actual value and probably just spoil your algorithm. However, let's now talk about those features A6 and A7. And remember, we say A6 would be a number of instruction observed between a branch instruction. And let's say A7 is how many branch instruction overall observed in a disassembled code, like percentage of the jump instruction over all other instructions. We can kind of our intuition tells us if it's a polymorphic code which based on spaghetti algorithm, it means it's actually going to have a very small number of instructions observed in between two branch instructions, right? Because it's a spaghetti. The whole point of it is split the regular code into little pieces. It's going to be on the lower side of A6, but it's also going to probably have a lot of jump instruction, right? Because to split the code on the instruction, you actually have to have a lot of jump instruction in the code. So if we plot malware, it's probably going to look like here, while the regular code would have much more benign code would have much more instruction between a branch instruction, and it probably would not have such a large number of branch instructions. Of course, once in a while, you're going to have exceptions where malware is going to look like this and benign is going to look like that. But when you try to separate them, you might actually have a pretty decent linear line, which would say, okay, based on this feature, we have mostly malware on the right side under the line and mostly benign on above the line. So that's why the logistic regression in this case, when the features are good and they're already representative about malware being malware or benign files being benign files, here in examples like that, logistic regression would actually work pretty accurately, because that, again, exactly what the expert would do before manually by assigning those weights to the specific features manually. Now, the expert would use logistic regression to assign those weights automatically, and it wouldn't just some sort of random weights from expert's head. It's actually going to be mathematically proven the most optimal, or at least closest to most optimal solution to split collection of benign and malicious cell using the features. That's why having a good, robust features was so important in those days of machine learning. And I argue it's still very important. Nowadays, we're kind of spoiled by deep learning and also CNN and RNNs, which can extract feature automatically, so we don't need to engineer them. But we're going to talk about this later when we get to these periods of time. However, I still think that for a robust algorithm, it's always very important to do feature engineering. It was true in 2005, 2010, especially because the algorithm itself was relatively primitive. It was linear based. I have to note here that there were the way to make logistic regression non-linear. That would happen when you would add, let's say, a 9, which equal to a7 multiplied to 8, right? So as soon as you start adding non-linearity between the features, like you can also add square, right? You get the square of these two and you multiply to each other. By adding more non-linear components in this equation, as you can see, the function is going to start to change, right? It might not be linear. It might represent some more complicated function. The problem with that is it's actually very hard to understand meaning of those non-linear components, and humans and even security experts are usually pretty bad in defining those components, so they would be just randomly coming up with the square and cubes and multiplication of different parameters, and what it might lead to is that the function is too complicated, and instead of separating these sets nicely, it might start do a weird thing like this, right? Overfit. And maybe it separates nicely in that training set because it overfits the training set. But as soon as you start adding more files in real life, you start to incorrectly classify things. This cannot be below 0, but you can start incorrectly classify things, for example, here as malware, even though benign files, just because it was optimized and overfit the training data. So again, it's important to know that logistic regression had that capability to separate the sets using nonlinear function by modifying the feature set. However, it was not always working well, mostly because, again, those features were not interpretable. They would be created kind of semi-randomly, and then the model at the end of the day would just overfit the test set, overfit the real production data. So very often, even if people would add some nonlinearity, it would be a very light sort of nonlinearity, so it doesn't overfit in some sort of crazy function, which then doesn't really work in production. So hopefully now you better understand how feature engineering was done in a period of time 2005-2010, why it was extremely important to spend time on feature engineering, and then crappy feature would not work at all. Weak feature, like string-based feature, might work on unpacked files, and there would be a very specific set of code-based, structure-based, some sort of maliciousness features which could work much better. They would be very similar to what used to be before machine learning in Heuristic, manually written, right? We would develop certain features, extract them, and assign weights. That's exactly what machine learning would do in case of logistic regression. But it would require training on a robust collection of both malicious and benign files to actually do it efficiently. Thank you for joining me today for episode about logistic regression and feature engineering. Hopefully you like it. If you do, please subscribe, share it with your friends,
share it with your colleagues. I will continue developing more content, and we're going to talk more and more about other machine learning algorithms in antivirus industry through the different periods of time. I'll see you in the next episode. Thank you very much.